In this video, we're going to be taking a look at two standing wave problems. We're going to solve for the frequencies of multiple musical notes for a clarinet and a guitar. For clarinet, we have this reed over here that acts like an open end, and then the bottom part that acts like a closed end. Now, when the clarinet is played, we'll go ahead and start off with the fundamental frequency. We have this closed and open end, and the closed end would have a node, and the open end would have an antinode. And then when you go to the third harmonic, it's going to go up by one small incremental change where you add a single half wavelength in the beginning. Now, when it comes to a closed and open end, it goes up by odd intervals. So it goes to the first, third, fifth harmonic, and so on. So here is the first, and then this one is the third. Now, basically how that works is for each chunk of the wave that looks like this, that sort of has this little eyeball shape, that is half of a wavelength. So we have half and then half of a half, which is a quarter. So we have 3/4 of a wavelength here, and then right over here we have a single quarter of a wavelength. Now, eventually we want to get to the point where we can use the formula velocity equals frequency times wavelength, and we are looking for the frequency, and we're already good with the velocity because we know it's 340 from the original question. So all we really need to find is the wavelength, and the wavelength for a tube that's closed on one end and open on the other is 4 times the length of the tube divided by n, which is the harmonic number. Now, in the problem, it says 66 centimeter clarinet, but we want to make sure we convert that and divide it by 100 and make that 0.66 meters. So the wavelength is going to equal 4 times 0.66 and then divided by 1 for the first harmonic. And then that's going to give us 2.64 meters. And then for the next one, we have 4 times 0.66 centimeters because it's the same clarinet, but divided by the third harmonic. So it's basically 2.64 divided by 3, which gives us 0.88 meters. Now our calculations for those are going to look pretty similar. We're going to have the same velocity of 340 meters per second because the velocity isn't going to change unless the temperature of the room changes. So that's a non-factor for this kind of problem. And that equals the frequency times the wavelength. And then for our second one, it's still 340. And that equals frequency times our wavelength for this one. So all you have to do is do a little bit of division for each one of them, divide both sides by 2.64, and divide both sides by 0.88. And then we have our two frequencies. For the first harmonic, the frequency is going to come out to be 128.79 hertz. And then for the third harmonic, the frequency is going to come out to 386.36 hertz. Okay, so first step is you don't necessarily need to draw each of these, but that's just kind of giving you a visual of what the waveforms look like within the tubes. And then from there, if you have something that has a closed and open end, such as the clarinet, then you're going to be using this formula right over here. And then plugged in the length of the tube in meters, plug in the n value, which is the harmonic number, and then you have your two wavelengths that can be plugged into the wave formula over here. Velocity equals frequency times wavelength, divide both sides by wavelength, and then you have your two frequencies of 128.79 and 386.36. All right, so let's go ahead and move on to our second problem, and then we'll compare some of the similarities and differences for our guitar problem. All right, so I cut up and scooted over of all of the main points of our first problem, our wavelength formula, our two wavelengths, and then our two final frequencies. Now for this one, it says a 60 centimeter guitar string plays its first and second overtone. What's the frequency of the notes played if sound is traveling at 343 meters per second? So again, we know the length is 0.60 meters once you take the 60 and divide it by 100. And we also know that the velocity is 343. So for this one, it's a little bit faster than the first one. Now, I purposely used the term overtone because that's one that wasn't used in the first problem. So when you're talking about an overtone, it's how many harmonics are above the fundamental frequency. So the first overtone is the second harmonic, and the second overtone is the third harmonic. So for a guitar string, let's go ahead and draw our first, second, and third harmonics. So the first one, it's going to be closed on both ends because it's either on the bridge where it's closed and then your fingers press down at a certain point, or it's up over here by the top of the instrument where it's still closed and there's no vibration. So we have one closed and one closed, and we go up by an increment of half a wavelength as we rise up from the first to the second to the third harmonic. Okay, and as I said before, this is the first overtone, and then this is the second overtone, which is what the question is asking about. Now for this one, if it's closed on both ends, then we're going to use the formula wavelength equals 2L over N, and we can find our wavelength for the second and third harmonic, which is our first and second overtone. So for the first one, the wavelength equals 2 times 0.60 divided by 2, and the 2's are going to cancel, and the wavelength would be 0.6 meters. And then for the second one, our wavelength is 2 times 0.60, and the second overtone is the third harmonic. So divided by 3, and that's going to give us 0.4 meters. Now from there, it's all pretty similar to the previous one. So we have 343 meters per second equals frequency times 0.6, divide both sides by 0.6, and then we have a frequency of 571.67 hertz. And then for the next one, again, looks pretty similar, 343 meters per second equals frequency times our 0.4 wavelength. With the greater overtone and the smaller wavelength, we're going to have a higher frequency. That one ends up being 857.5 hertz. So working out problems like these, sometimes it's helpful to draw out your different standing waves, so then you can get a visual of what's going on there, but not necessarily based on what the question asked us. But if you have harmonics, then you just basically go from first, second to third. If you have a closed and open one like the clarinet, then you go by odd increments, so the first, third, and then fifth harmonic, and then so on. And then from there, what you do is you find the wavelength using the proper formula. We had the 4L over N for the open and closed tube. And then for this one, this is for the closed and closed for this string. This one isn't necessarily a tube. And then you plug in our length in meters, our N, our harmonic number. We found our wavelengths, popped it into the V equals F times lambda formula, and we're able to find our two frequencies that way. So I hope that was helpful in helping you set up some standing wave problems, finding the wavelength, finding the frequencies. Thank you very much for watching and listening.